Hello and welcome to the Printed Circuit Podcast, where we discuss trends, challenges, and opportunities across the printed circuit engineering industry. Joining me today on the podcast is Are Halvorsen, Principal Design Engineer at Microchip. Welcome to the podcast, Are.
Thanks for having me, Stephen.
Yep, it's great to have you today. Could you start by telling the audience a bit about yourself and your role at Microchip?
Yeah, so I work out of the Trondheim office in Microchip. We're about 100 people. I lead a team of 4 other engineers, and we create eval boards, development boards, EVKs, for Microchip's new silicon products, mainly microprocessors and microcontrollers, but also other types of silicon.
Can you tell us about your background, basically how you started in the industry, how you evolved and how you ended up at Microchip, at this role at Microchip? Because I know you guys are doing some fascinating architecture there.
Depends how far I should go back, but I was a 15-year-old kid at some point, and I said, you know what? I'm bored of school. I don't want to do this anymore. So I started training to become an electrician through the equivalent of high school. I got to a point where I actually was offered a job as someone that installs telecommunication equipment, an apprenticeship. I had a teacher back then that pulled me aside and said, Are, you know what? You don't want to take this apprenticeship. You should become an engineer. And I told him, so what's an engineer? I didn't even know. I had no idea. So I was bored with the framing of high school. So I went to the university. I did all the maths and chemistry, physics. I met 2 very engaging teachers that really got me interested in science again and maths. I applied to become an oil drilling engineer. It's a master's degree, and there are 10 spots in the country every year. I got in, and I figured out, you know what? I don't want to be an oil drilling engineer. So, after all, so I started electronics, started a bachelor's degree. I found an open spot, no requirements, just sign up, get going. So I did my bachelor's. I wanted to start automation, working with PLS systems and things like that. So I applied to do that. But I hit the wrong button in the web interface, and then I ended up with electronics. And that's where I learned about microcontrollers. That was my first introduction to microcontrollers during my bachelor's. And we were lucky enough to have a company called Atmel locally in our city. And this stuff fascinated me. I thought it was really great. So I contacted them and said, you know what? I want to work for you guys. I was lucky. I got a bachelor thesis with Atmel. I got an internship where I got to meet a lot of great people, applications engineers and others that did hardware, studied digital chip design, did a master's degree in that, but I've never worked with that at all. So I started full-time in Atmel in 2012, doing eval kits. We were acquired by Microchip in 2016, and I've been here ever since.
What a story. My goodness. I love the fact that you started in one direction and then you pivoted, a few times. And I think many of us in the industry, we kind of navigate uncharted waters and your career just unfolds. And if we were to look back at that young kid that started 15, 16 years old, we would have never guessed this is where we were ending. I love it. The first thing I want to get your thoughts on is, can you share with me the basics of how your high mix, low volume turnkey operations works at a high level there, at Microchip?
Yeah, I can talk a bit about that. So we can start with how things are operating today. I can talk a little bit about approaches we tried before that didn't really work or scale at all. We have a team of, let's say, 15 people in Asia. They are our operations team, and they ensure that we manufacture more than 2,000 circuit board products using contracted manufacturers. So these guys are the real, heroes of our operation. So when I do a design, I make sure it works. We get the prototypes back. When we release it, I don't hear about that design ever again, unless there's a problem. That's kind of the philosophy we want to go for. As long as we do our jobs right, then the operations team can then make sure that it manufactures and that it's stocked in the shelves, and we can focus on whatever's new. How do you do that? That's, it sounds great, but how do you even do that? We have a common component library used across the company. People do their hardware design with that component library. If they're missing parts, they obviously have to add the parts into the library. They complete their design and they generate production package that is, let's say, standardized. They upload the BOM, they provide it to the operations team. They give a review and say, okay, everything's in order. They ship it off to the contract manufacturer. They do their thing. They handle procurement of components. They handle assembly. We also work with a dedicated PCB broker, so not an individual PCB manufacturing site. We do that because we are able to scale. We can manufacture at different locations. We can, if a factory stops working for whatever reason, we can just move a design to another factory. That's also a key thing in this. We get the prototypes back. We validate that the design works. We develop automated manufacturing tests using Python, and we talk to our hardware. We do some self-tests. We do that in test fixtures that I draw up electrical connections, and the contract manufacturer takes care of the physical part of it. Then we do a first article or series 0 build where we qualify everything. I get a piece of hardware back and I'm asked to say, you know what, this is good. Once I approve that, it's in the hands of the operations team. That's kind of the short version of how it works.
It can go really deep when you think about the overall process of designing a circuit board, especially when you're dealing with multiple teams in multiple locations and you got the whole gamut from your supply chain, external stakeholders, which is your fabrication and your assembly team. And it takes a lot. It's a lot of communication that has to go on, a lot of collaboration and integration of how you're handing off and how you're exchanging. And if you're not following the industry best practices, it can definitely be very expensive, meaning time and money. And then you don't communicate correctly, or you don't get all the information. Next thing you know, you're forced to do a respin because you missed something. You definitely have to follow industry best practices. And it sounds like what you guys are doing there is state of the art, and you guys are on top of it, especially with the success you're having there at Microchip. You talked about manufacturing. So as an engineer, let's go to our next topic I want to talk about, which is design for manufacturing and turnkey manufacturing tests. Can you elaborate a little bit more of your process and how you guys are addressing, DFM or design for manufacturing, and then the turnkey manufacturing regarding, testability?
I think the first thing about DFM is you have to think about it from the start. I think that's the key mistake that people do. You have to know the capabilities of wherever you're assembling your board. Let's say for us, that's a contract manufacturer. We know that they can provide automatic image inspections. We know what kind of problems you can catch with AOI. If we have a really big complex design, we can ask them to do manufacturer defect analysis, so MDA. You basically build a huge bed of nails fixture, and you have a piece of electrical measurement equipment that does a matrix of measurements between basically all the needles, resistance, inductance, short circuits, capacitance, that type of thing. You take what you call a golden sample, you profile the board. So they don't even need to know how the design works. They just profile a board works, and they compare those results to new boards that you make. So you're making an electrical profile of the design. You don't need that for really simple stuff, but if you have a board with lots and lots of connections and nets, then that can kind of make sense. What we do differently, I think, is what we call the fixture test. We don't have pre-made solutions with $1 million equipments and flying probes or anything like that. But we make sure that in the design phase, we put test points in critical areas of the design. For MCU board designs, that's typically you need access to your programming pins. That's a given. You need access to measure voltages around the board. If you have any power supplies or anything like that, maybe you want to measure inputs, outputs. You want to measure, since I work with eval boards, there's always USB, right? So I have a luxury of always having USB on my product, which means that I can measure the current that goes through the USB cable, can look for short circuits before I connect it to a PC. So I have a luxury there. We put this board in a custom-made test fixture that connects everything you need. And we have a Python framework that is a GUI that the contract manufacturer uses. From their point of view, that GUI is the same for every product. It's very simple. You open the GUI, you have your barcode scanner, You scan your serial number. The GUI takes care of downloading the appropriate test software if it's not already on the computer. You hit the big play button. You know configuration. Those guys, they don't know the product. We do. There's one big play button. Once you hit the button, you wait. You see the test progress. When it's done, it says passed or failed. That's it. So we own the production test, not the CM. And in that way, if things fail, they say, you know what, we're having a lot of failures. Please go look at the test logs. So we can go look at the test logs, look at the parameters. And worst case, we can also do remote debugging. So I can log into the test station remotely, and I can kind of work with the technician and figure out, or their test engineers, to figure out what's actually wrong. So I've been able, through that setup, without having access to, any measurement equipment or oscilloscopes or anything, I can't touch the hardware. I've been able to pinpoint things like LDOs being mounted wrong. I've been able to pinpoint things like we made a design error, we swapped the ground and the power pin on an IC, things like that. So the test logs and the collaboration with the test engineers can give you a lot of insight. It's really hard to debug without equipment.
I totally understand, because as a technician, early in my career, being down in the lab, troubleshooting, and I refer to this like chasing the dragon. You're trying to find a needle in a haystack. You're trying to figure out why it's not working. Sometimes it's straightforward, it's easy. Other times you could be there for weeks and you can't figure out. It's very difficult to figure out what's working. It really excites me when I hear you talk about the testability regarding DFM in regards to your NDA, which is your analysis that you're capturing, your bed of nails. I mean, those fixtures, those bed of nails fixtures, especially if they're clamshell, they're not cheap. I'm curious, your test points, you mentioned test points on your boards. You put them on strategic locations. Is that correct? You don't do 100% on every net, just on specific locations. Is that what it is?
It depends on the design. So I can actually show you a couple of designs right now, where I can show you the difference.
For our audience, you can't see because this is a podcast, but ours got a unique setup where he can show us some circuit boards. So we'll kind of talk through this and hopefully you can visualize. He'll try to explain in more visual effect of what he's showing.
So this is a really, really small design. There's not a lot of room on this design. You can't have 100% test points here. On the other hand, the design complexity isn't that huge either. So on this board, I don't do any MDA testing. There's no electrical profiling on the board. There's AOI going on, so you can catch a lot of soldering defects. Obviously, you're not able to see defects in BGA packages or QFN packages without wettable flanks, things like that. So our approach to testing basically said that when we made this board, we figured out, okay, if I know I can't see under those packages, can I do some functional testing to infer the fact that it works? And that's exactly what we've done. So if you see the larger QFN next to the USB cable, those small DFN packages next to it, and all the circuitry over there, that's actually an embedded debugger on this board. So this part of the board connects to USB, and it lets you program and debug the actual chip we want you to evaluate. And that's the small one on the other side. By connecting to the outputs of the power supply, by connecting there, we know that all of those small DFN packages actually are soldered correctly. We measure outputs from the LDOs on the board to verify. So part of that functional testing also involves having the embedded debugger on the board program the target, being the PIC MCU in this case. We load special firmware in the PIC MCU that exercises all the lines, the connections between the PIC MCU and the onboard debugger, and the debugger reports back through USB. So we've taken a design where we have a lot of small parts, like there are electrical level shifters here that are 6-pin miniature packages. I can't do that with AOI, but we infer it from actually exercising those pins in our test setup. We mentioned that this is low volume and high mix, right? 2,000 plus products. So test time isn't that critical, right? I don't need to test this board in a millisecond. I don't need to test this board in 1 second. I build them in batches of 500 to 1,000 at a time. So, okay, the test takes 20 seconds. So what? Doesn't matter. If I was doing something that was really high volume and I needed to get my test time down because it was important for the margin, of the product, I wouldn't have that luxury. So when you test silicon, you can't do it that way. You can't spend 20 seconds testing a piece of silicon. If you do that, you can't sell the product. Nobody wants to buy it. It's too expensive. On the flip side, you can see the test points really. So the test points that I'm pointing at here, that's the programming lines for the debugger chip. So that's our entry point into the whole board. Program the debugger chip with a bootloader and firmware. Then you go in through USB and you do some voltage measurements over on the edge. That's enough I can confidently say that this board works 100% when I bring it out of the fab without doing any electrical profiling.
I really like that board. The look of it, especially, me being 35 years of designing, I've seen several different type of test boards, and I really like the castellation on the edges. So you can mount that on another board if you had to, or solder it down. The way it's condensed. I mean, we talk about today's complex packaging being smaller and tighter. And I mean, that's a perfect example of a very small test board that you're able to do, it's a really good functional test, especially through the USB, what you're doing there. I'm curious, when you generate these boards, are you guys utilizing ODB++? Are you guys, for your manufacturing outputs, or are you guys using 2581? Or are you still using standard Gerber with netlist?
We're still on the Gerber train.
No, it's something wrong with it. I mean, it's still the highest demanded outputs is Gerber. Gerber data is still in the industry today. According to iConnect 007 and PCEA, these two different entities have their respective magazines and their research they do. Gerber data with the netlist is still the number one requested output data. But, with the intelligent formats, we can do a lot more. Let's talk about problems, especially when we talk about scaling these kind of things to processes, to different teams and locations, because you mentioned, you have 15 designers in Asia or 15 people in Asia. So you're all in different locations. Talk about this, the scaling these kind of processes.
So back when I started, you can kind of bring it back to when I started my career in Atmel. I was sitting in a room with 3 other applications engineer, hardware designers, or not hardware designers. They were application engineers. They knew how to do hardware design. They knew how to do high-speed design. They did firmware development, code frameworks to let customers code their own applications. They released examples. They wrote user guides. Everything. It's everything from A to Z. So, one thing is creating the actual piece of hardware, but if you want our customers to use it and learn something from it, you need to provide actual firmware and documentation. A big part of the job we still do in the team I run is exactly that. It's not just hardware design. I don't want to say just, but it's more than that. The team I joined was very cross-functional. We had people that knew a lot of different disciplines. We had programmers, we had people that made traditional debuggers, right? Tools that you buy and you plug into your own hardware and you program and debug your own hardware. Those guys were combined into the team of applications engineers and designers, and that's when we invented or created these onboard debuggers that I was referencing. You need a lot of different disciplines. You need deep knowledge of the silicon and the debug systems. You need deep firmware knowledge, and obviously also how to design the hardware. So that cross-functional team developed these kind of complex boards. We started with something like this. This is a credit card-sized board that let you evaluate a microcontroller. It had some sensors on it, some capacitive touch, and some different things. The problem with them is you always had to bring a debugger. So if you went to a training session, this board is quite cheap. You can manufacture it, but you still need a debugger. This is a $100 tool. So, okay, what can we do about that? So this cross-functional team just said, okay, let's just put the debugger on the board. Easy enough. We did that. We created some more scalable boards like this. Here we hid all the debugger circuitry on the bottom. Still needed a lot of tinkering from different people to get it working. We progressed to more advanced stuff, more peripherals. Here we have Ethernet and other things. Still the same thing. There's a debugger on the bottom. This thing you could also at the time get for around $50 instead of buying, a expensive development kit and a $100 debugger. But in order to get all this to work, you needed to master a lot of disciplines. You needed to master hardware design, high-speed hardware design. You needed to master firmware development. You needed to understand the manufacturing process, DFM. We needed to comply to our in-house product lifecycle management systems. Architect of that system happened to sit in the same room as well, right? So we were in this bubble where we could do everything locally and have a good connection with one team in Malaysia, in Asia. That was the operations team. That's a luxury you don't have all the time. That's where the scaling problems start. So we were able to scale this to a design team in India. They made the same type of products. They became highly efficient. But the only way that happened is we talked to them every day. That's what we needed to do because we were doing so many different things. You know, you can't just give this to a hardware designer and say, make this. There's a lot of things to do. That's when we kind of realized back then we had in our design flow or production flow, we had a lot of gating steps. So there were formal gating reviews. So I ended up being one of the people doing those formal gating reviews. So once a week, I sat down, myself and one other engineer, and we looked at submissions from other teams. And our job was to figure out, did they follow the process or not? It's quite time consuming. It's frustrating for the people on the other end if they did something wrong or, you know, they forgot something. So it was quite a tedious process and not very efficient. To be quite frank, Atmel had about 6,000 employees, a lot of different business units. We were able to scale this to a team in India and 2 other teams within the company. Everyone else just said, you know what, this is too hard. We don't want to do this. We'll set up our own CM. We'll deal with it ourselves. We'll get you the hardware. We'll get it to the warehouse, but you don't get a say in how we do it. That's the drawback of creating these complex processes, is that if you have someone with hardware experience that really knows how to make a good piece of hardware, they don't necessarily know the rest. That was the Achilles heel of how we did things back then. The difference today is that we don't really have a lot of gating criteria anymore. So whenever you start a design in our system today, no matter if it's a prototype on your desk or if you intend to mass manufacture it and sell it, you start the same way. You go into a self-service system, you generate part numbers for your PCB, for your product. You can do that yourself. There's no one that needs to approve it. Then you start working on your design. That's in a component library. You can put things inside the component library yourself. There are no blockers there. People need training in being a library manager to formally approve components in the library, but everyone is allowed to put a component in the library and put it into their design, even if it's unqualified. No blockers. So that's the approach, right? Self-service all the way, no blockers. That's how we do it. The analogy I would say for our process is it kind of flows like a river. You start at the beginning. You do what you need to do. You create your part numbers, you create your library components, you do your design. And when you're done, you have a package in your hand. You drop that package in the river. And if you've done your job right, it flows through the river and it, ends up in the warehouse. That's it. That's the truth with modifications, right? There are some checks and balances. So we do have a review of the bill of materials before we actually let the package be dropped in the river. That's one. We also have a gating criteria where you need to justify why you're making this product. That's number 2. And you also have to, once you get your prototypes back, you have to put your stamp of approval on it. That's basically it. That's how we've been able to scale it to more teams without enforcing how you do it, but we enforce how the files are generated, stored, and managed, so that that small team of 15 people can deal with all the products in the same way, even if it's like a small board that I showed you first or a huge complex $20,000 FPGA product. It's the same process.
That's awesome. It's interesting because when you think about the multiple domains collaborating in your tools and especially library management, I'm curious, what are the things you're looking forward to get easier, as you implement or you're running with the Siemens tools or the Siemens solutions, specifically with like EDM and the collaboration you're doing? Yeah, I'd like to know your thoughts on that.
Right now, my team, we store our design files in Git repositories. We do a lot of software development as well, so we're comfortable with using Git. That's not true for everyone. Everyone stores their files differently. The consequence of that is if someone comes to me and says, can you tell me which design files were used to generate this output? I can point them to a specific Git hash and say, this is the place it got from. But again, software development. More traditional hardware development engineers may be using Windows shared drives, or God forbid, just put it on their local PC. Put it in OneDrive, wherever. But they might not necessarily be able to point you to the exact design files that were used to generate the output. That's a problem, right? So when we do the design review, for instance, we have to generate PDFs. We send the PDFs to a bunch of people. It's hard to comment in PDFs. Maybe you need meetings to actually sit down and start circling with pen and paper. And that process is quite cumbersome. When we release design files, I mentioned we have standardized production packages that you need to upload. The bill of materials and all the Gerber data, the drill data, PCB specification, all of that. We can't control how everyone stores those files. So people need to follow templates. And maybe it's not exactly how they want to do it. They need to do it outside the software, outside the toolchain. They have to manage files, and that's a complication. Even the component library. The component library, actually, it lives in a Git repository now. To a lot of designers aren't happy about that because Git is complicated. I'm looking forward to baking all that into one system, into one toolchain. Once you have it in one toolchain, that's how it works. It's all in there. You open your application and you work on your design, and it's just built in. When you're done with your design, or even along the design, you save your thing, and the toolchain takes care of tagging, revisions. It takes care of saving all the intermittent steps. Whenever you're done, and when you go to review, you have an integrated solution where you just point someone to a website and they can start opening the design in the browser. They can comment. You can see statuses on different topics that you had to deal with. You can, all that traceability is in there. It's in the toolchain. When you're finally done and you kind of hit the approve button, we're now able to have the system generate the output the way it should be and automatically upload it into the lifecycle system without having to manually manage files or teach people how to do it. It just works. That's really lowering the bar for the engineers to be able to focus on what they really know, and that is hardware design. They know their products, they know how to do it, but they don't have to be bogged down by all those extra things that you need to do today to get a design in production.
When you think about a well-oiled machine, that's what Siemens offers is a fully self-sufficient ecosystem that allows you to focus on what you do best rather than having to be forced to do a lot of manual steps, which anytime you have manual steps, you increase your potential for errors to exist or to be created, especially if you're dealing with just PDFs and people commenting in PDFs, getting red lines. And, I have many of experiences where stuff just gets missed, where you don't have any gatekeepers or any phase gates to know, did everyone collaborate or did everyone comment on it? Did all the feedback come in? And you end up missing something. And you end up, causing a forced rev, or even potentially you create the wrong version of the board because you miss communication. Yeah, it happens. It happens to the best engineering teams today. So we're running up on time. So let me get your final thoughts. What are the final thoughts you'd like to share with our audience? I could keep talking to you all day, especially when I see all that equipment behind you and the circuit boards you showed us. I mean, I wish the audience could see what I'm seeing, but what are your final thoughts that you'd like to share with the audience?
We're in an interesting industry. Our industry has consolidated over the last few years. You're seeing fewer and fewer companies, but there's still so much innovation going on with customers. The possibilities are almost endless. Today's buzzword is data centers and AI, but there's always going to be a new thing. That's kind of what's kept me in this industry and this job in Microchip. It's like the constant change. Constant change really fuels me. It makes me motivated, and it really wants me to get up in the morning and go to work and, solve problems. That's essentially what engineers do, right? We solve problems. Sometimes we find too many problems, but hey, let's try and if we focus on the problems and we solve the problems, then there's endless possibilities of what I can enable other engineers and companies in the future to achieve.
That's awesome. That's awesome. Well, like I said, we're up against the time. And I want to thank you for joining me today on the podcast. And thanks everyone for tuning in as well. To our audience, please continue to tune in for more trends, challenges, and opportunities across the printed circuit engineering industry.